Thanks very much. So I talk about the organic-inorganic carbon interactions today. And Paul already pointed out this morning, if you have weathering processes, you change the soil chemistry. And so what we're looking at mostly in the inorganic carbon space is the bicarbonate formation. But what you also have is pH changes, and you release cations. And eventually, over the long term, you also provide mineral surfaces that can then change, for example, the soil organic matter stabilization. So overall, all of these processes in some way modify stabilization of organic carbon and also decomposition reactions. And that's what we'll talk about today. First, a bit about how can we measure it. So to change, and I'm going to use soil organic matter and soil organic carbon interchangeably, which technically isn't right, but that's simply, you'll find it probably on the slides, possibly mixed up as well. But generally, to measure it, you can either measure stocks or fluxes. So stocks usually then the total organic carbon content. And the problem with that is in field trials, you have really a large spatial heterogeneity. And also huge changes with depth. That is a big problem, and I'm working in the field trial that I have is in a forestry system, and in the forestry system, it's even larger changes spatially than in agricultural systems because they mulch in the residues, and so you've got peaks of organic carbon throughout spatially. I mean, in pot trial, it's still a problem. Even in in soils that you homogenized, you have heterogeneity. And so to detect changes over short periods is really challenging. Flows, on the other hand, usually as a net ecosystem CO2 exchange is a lot more sensitive. The problem is you don't actually know which of the stocks changed. So soil inorganic carbon, soil organic carbon. And there are a few papers out there. One paper that actually measured fluxes, and they said they didn't see a change in organic carbon, so everything must be inorganic carbon changes. And there is a paper that says exactly the opposite. They used the method, and they said they didn't see any inorganic carbon change, so it must be organic carbon. So literally papers that were published in the last 2 years, they used this method for basically having a look at two different mechanisms. So clearly also tricky. And you have got a lot of plant-soil interactions, so plant respiration, so root respiration, above ground respiration, photosynthesis. And so you're not actually sure what actually happened, and it's difficult to differentiate. So what I do is I do a soil organic carbon fractionation, which basically is a stock change, but you're having a look at different carbon pools. And the advantage being, first, it's more sensitive than total carbon change, but also you can have a look at pools of different stability. And so you already get an idea about the mechanisms, what actually changed, how it changed, and so you have a more depth understanding. And so here, we've got the different carbon pools, essentially, showing both the stocks and the flows, and particularly organic carbon being the least stable carbon pool, which comes from recently plant-derived material in some way, usually quite macroscopic, so you can see those once you separate that from soil. You've got organic matter in aggregates, and you've got dissolved organic matter or low molecular weight carbon, and then that sorbs to mineral surfaces. That's the most stable carbon pool. So using that method, I did a pot trial in 2021 during some lockdowns at the time. It was very difficult to maintain a plant trial. And now we're looking at 3 carbon pools here, particularly organic matter, aggregate carbon, and mineral-associated organic matter with increasing stability. Looking at a baseline here, and then over 6 months, essentially without any plant in the system, without any rock at this sort of reference system, we've got a loss of particular organic matter, which is totally fine. It makes sense. We've got water, we've got decomposition reactions, so you lose it. Now, when you put rock into the system, we reduce that loss. So we still have particulate organic matter being lost in that way, but it's actually transformed into more stable carbon pools. So the rock did something in the system that the organic matter was stabilized. And that's great. We had both of the more stable carbon pools higher. But the thing was, it was more complex. So here I'm only showing 2 treatments. I actually had 12 treatments in here. A lot of different things happening with different water amounts, of how plant, no plant, rock, no rock, and even a microbe added. And so overall then full factorial 12 treatments. But in the end, the plant actually partially counteracted those effects. And I'm not showing the bars because it's simply too complex. And bottom line here being, there are more reactions, biology, chemistry, interactions, and we don't fully understand what happened. I had a few hypotheses, but it's certainly complex. Now here, a new trial, they're using 7% rock in soil, which is a high amount, but it's actually mirrored a field trial. So in the field trial in forestry system, I had 5 tons per hectare, but concentrated in the rib line. And so then instead of having 5 tons per hectare, I had 90 tons per hectare. So essentially, that was then the trial that I mirrored in the pod. And here we again have a soil baseline, but now also a soil rock baseline, because we add quite a lot of rock. And the first effect is actually dilution effect. We look at soil organic matter, and we add a material that doesn't have soil organic matter in it, we dilute it. So that's very important to take into account, and I'll talk about generally on the next slide what implications that has. But now after 22 months, we've got an increase in carbon pools, because here this is now a system with plants. So basically we've got all of these are pine planted. So basically we increase, these are small pots, we increase soil organic matter, that makes sense, both because of the pine residues and exudates as well. But we've got a particular organic matter loss in that time. Control versus rock. And if we now bring that into context, how large that loss actually was, the change in CO2 versus the baseline versus the control. If we first look at the potentially inorganic CDR based on soil exchange with calcium and magnesium, I'm not talking about inorganic carbon because the inorganic carbon story was even more complex, but overall, the loss of particulate organic matter was a lot larger than the potential gain in CDR. Just highlighting how important it is to have a look at soil organic matter pool. And if we now look at it more sort of holistically, there is a recent meta-analysis from last year where they had a look at all rock amendments, all sorts of rock amendments, including lime. And they overall showed there was an increase in soil organic matter by around 4%. So I wasn't part of this meta-analysis, and 6% in mineral-associated organic matter. However, basalt decreased soil organic matter. Problem here being, I'm very sure this is a dilution effect, because very few people actually have a rock baseline included, because it's very, very difficult to measure a rock baseline, in particular in field trials. So if you have a dilution effect, you have no baseline, you don't know actually that you diluted it. So they had an 18% decrease in mineral-associated organic matter, which makes sense because fine rock accumulates in that fraction, and also the more rock they applied, the lower the soil organic matter was in the end. Which, surprise, if you apply more of a material that doesn't have a particulate organic matter or SOM in it, then you decrease the pool overall. But as my study also showed, there are increases in soil organic matter. So if we look at it, reactive mineral surfaces that we form can sorb soil organic matter. We have polyvalent cations that can help bridge dissolved organic matter to surfaces. So we can increase mineral associated organic matter and also aggregates. And then we also have better plant nutrient supply, which can help bring more carbon into the system. But in my trial, the reason why there was such a massive decrease in particulate organic matter was a simple pH effect. And I said I had 7% rock addition, and there was quite a bit of pre-weathered material in there. So there were carbonates in the material. And when I did the calculation, I applied, so based on a lime equivalent, it was something like maybe 500 kilograms per hectare. So basically, I simply limed the soil initially, increased the pH from something like 5.5 to 6.5, and so you massively change the microbial composition, you decompose particulate organic matter. And then that is very well known. So here just a study, a really good review at the right bottom, showing that you've got the positive priming effect at that sort of pH range. So you simply decompose particulate organic matter in particular. And so then you've got also, in my previous study, I showed you can decrease micronutrient availability simply because Micronutrient availability is very sensitive to pH changes, and so then you've got these potential interactions with plants and microbes. So overall, the system is complex. We're talking about soil texture, mineralogy, starting SOM content, plant carbon, microbes, and then some sort of climate effect or a local effect with precipitation, with temperature, and then obviously the rock type as well, which we already talked about. And now, sort of briefly, what this means now for CDR. So initially, when I started with the research and had the first experiment, I was hoping, ideally, what scenario we might end up with is we're going to have initially the emissions from rock mining, grinding, and spreading. You can't see that's right. And then we're basically going to have inorganic carbon formation, and so eventually we're going to get through the threshold and basically then have actual removals. And then if we have the soil organic matter on top of that, overall, with those synergies, we simply have CDR from both inorganic and organic carbon. Now, the reality was the second experiment showed the opposite. So we started with technically then the emissions from mining, grinding, and spreading, and then we had a very small inorganic carbon signal, but some soil organic matter was lost. And so it has the potential generally to release more CO2 from those soil organic matter pool than was captured with inorganic carbon. Now the reality probably looks more like this. Timescale, and we just talked about this. Very important to take that into account. Because those SOM decreases because of pH are short term, it's about basically nearly you're going into an optimized system at pH, let's say 6.5. Where you then have more carbon produced from the plants, more carbon going into the system, and then also more turnover, more conversion processes, and more stabilization. So in the end, it's really a matter of time, looking at the system for longer. And then you have more mineral surfaces, really reactive mineral surfaces, and can form more soil organic matter over time. But the tricky part really is to get those long-term experiments. And we don't fully understand everything, but as I showed, we have a good idea, particularly pH being a really important factor. And so talking about models this morning, for this, for example, we do need, ideally, we have a model, but we need more data, and specifically field trial data and data over a longer time to then be able to be confident so that we can then overall tweak the biology and the chemistry for both maximum inorganic carbon and organic carbon. Thank you very much.